Okay, here we're carrying on with topic 1, physical quantities and units. Now, what we're looking at here is homogeneity. Now, homogeneous or homogeneity associates itself with these base units. It tells us if something is homogeneous, then the equation can work. The reason for that is if you look at this equation here, the equal sign, okay, that tells you that both sides of the equation mean the same thing. So this side is velocity, that means this side is also velocity. Okay, so both sides have to be the same thing. So that means if both sides of the equal sign, the units are the same, then we can say that the equation will work. So in this case, if we put in 10 meters and 10 seconds into the equation, we get 1 meter per second, and this side we also get 1 meter per second. So we're saying that because of those units there, they both have the same meaning. Okay, we're dividing here, we're dividing meters, dividing by seconds. Okay. Now, another way of looking at it is, let's say we've got these two cubes, okay, or let's say 2 squares. Okay, so we've got one square there, and there's some dimensions on there. So A is the height of this square, so we'll call that square A, that one's square B. So A is the height of square A, and B is the height of square B. Now, for me to find the area, then I must, this is for the total area, I must add the two areas. Okay, so length A squared plus B squared. Okay, and if you look at the units of these, area is measured in meters squared, or it could be centimeters squared or millimeters squared. Then if we're using A, it's actually got the same unit, and then B, it's also got the same unit. Okay, so that we can actually say that this equation works. However, if we wanted to do this one here, where we've said area is equal to meters squared, and tried to add together another area plus a length, we cannot do this, because that does not end up being area. It ends up just being nothing, of no meaning at all. Okay, you need to add area to area, length to length, time to time. You always add the same thing together. So homogeneity checks to see if the units on each side of an equation are a match. If they do, we can say that the equation is homogeneous or that it works. Okay, let's look at this example here. Okay, so famous equation equals mc squared, where E is energy, m is mass, and c is speed. What we're going to do is derive the base units for energy on one side, and then derive the units for mass times speed squared on the other side. So let's look at energy. Now, first step would be, let's find a formula. Okay, so work equals force times distance. Now, like we've done before, I didn't know what force was, so I could also use F equals ma. And I can then put that into the equation for force. So I get m times A times D, or mad, and I now know the units for these three terms, all in base units. So I can put them straight in. So I have kg ms to the negative 2 multiplied by another m. Okay, and that equals kg m squared s to the negative 2. So that's my derived unit for energy. Now that's using the defining formulas. W equals FD or FS later on is the defining formula for work or energy, and using other equations for force we can then find that derived unit. Let's look at the other side. Mass times speed squared. So mass is, let's write it here, so m times c squared. Let's put in the unit straight away because I do actually know what mass and speed are in their base units. So kg is mass, speed is ms to the negative 1. So it's all in base units, m and s, and I am going to square that. So this is the same as m1 s to the negative 1. When you square it, you multiply the exponents. So you get kg m squared s to the negative 2 as my total derived unit for the right-hand side. What do you know? These two equations here and there are equal, so we can say that the equation is homogeneous. Now what we have here, we have another example, different equation. So what we're going to do is head through and maybe solve this one. You can see this one has three terms. Now if you think about it like that area equation, then essentially we have to say that this pressure there is going to be equal to pressure plus pressure. Okay, so all three of those should be pressure for this thing to be homogeneous. So let's have a look. What is the base units or the derived units for pressure? Now we'll use the defining formula for pressure, which is force over area. Now force is mass times acceleration. We actually know what this is. kg ms to the negative 2. We're going to divide that by meters squared. So simplifying this, meters squared goes to the top line, and it's going to be 1 minus 2, so it makes minus 1, and we have s to the negative 2. So that's your base units for pressure. Now, maybe we now look at half rho v squared. Now I'm going to ignore the half. Why? Because it doesn't have any units. So let's just look at rho v squared. Okay, now rho is density. We could use the formula, which in fact we might. Density equals mass divided by volume. So this is kg m to the negative 3. Okay, so we're going to put that into the equation here. So we have kg m to the negative 3 multiplied by ms to the negative 1 squared. So let's see what we get there. We get kg, we're going to have m squared and m to the negative 3, so that makes m to the negative 1, and we're going to have s to the negative 1 squared, which is s to the negative 2. So far so good. Okay, we got the same derived units as the original pressure there. So let's look at the next one, rho gh. Now, already done rho. G is acceleration, h is height. So in fact I know all the units for these in base units only. So what is density? Is kg m to the negative 3, okay, mass per unit volume. Going to multiply that by ms to the negative 2 multiplied by m. So we have kg, we have down negative 3 for m, but we're going up 2. Okay, so we have m to the negative 1, and we have s to the negative 2. And what do you know? This equation is homogeneous. Now the next thing we can look at is prefixes. Pretty much we're attaching something to a unit, for example, millimetre. We're attaching a prefix, or centimetre, attaching a prefix there to change the size of the unit. Okay, so instead of a metre being a certain size, putting centimetre in front of it means that if you have one of it, it's a much smaller thing. So let's have a look at these. So prefix symbol, going down the list, the symbol for pico is small p, small n for nano, micro, which is the only one with a Greek letter, is mu, milli, little m, centi, c, deci, d. We don't really use deci much, okay, so not too important. Kilo, K, mega, capital M, giga, capital G, and tera, capital T. Okay, so those are the ones going down. Now, the good thing about what you might need to learn is the sets of threes. If you actually try on your calculator pressing the E and G button, the engineering button, you see it changes the size of the value by a exponent of 3. So let's try and have a look at what the size of pico is. It's actually going to be 10, something multiplied by 10 to the power of negative 12. Okay, now if we go up 3, we get to -9, which is nano. If we go up 3, we get to 10 to the -6, which is micro. Go up 3, you get 10 to the -3, which is milli. And going down the other way, times 10 to the 3 here for kilo, times 10 to the 6 there for mega, times 10 to the 9 there for giga, and times 10 to the 12 there for tera. And a couple missing here. Okay, centi is 10 to the -2, and deci is 10 to the -1. Okay. Those we won't go too much into because you should really know them by now. Now, estimation. What I'm going to require you to do is we'll do this in class, but I might go through some of them now. So what you're going to do is you're going to do just a table with your quantity, estimates, and some measurements. So here's some here. So if we're looking at the height of a bench in a room, let's say it's around about waist height, and then like a normal, let's say it's about my waist height. I'm about 1.8 meters, so it must be around about a meter, okay, at a guess. Okay, height of a room, let's say it looks to be not twice the height of me, it's probably about 1.5 times me, so let's say around about 2.5 meters. Length of a pen, okay, well this one you need to know your centimeters well, where you're probably going to have your ruler with you, so it's probably going to be quite handy, but usually length of a pen is around about 10 centimeters or so. Diameter of a pen, around about 1 centimeter. You can see here I'm not being too precise, I'm just putting in values that are approximately right. Mass of a ruler plastic, it's around about 30 grams probably. Okay, this is just a guess, I guess it's about there. Volume of a head, that's a good one, we'll probably do that in class. Mass of a person, well, just think of yourself, you know, probably add a bit for the general population, so let's say probably around about 70 to 80 kgs. It's rising every year. Mass of a car, yeah, generally around about 1.5 tons, so in kgs, probably about 1,500 kgs. Acceleration due to gravity, we all know that it's about 9.81 is probably the actual figure, but we're just estimating, so let's say it's 10. Size of an atom, the size of an atom is about 10 to the -10, okay, so pretty small, but then the nucleus is even smaller, 10 to the -15. Wavelength of visible light, something you need to remember is actually the spectrum, but that's later on the year, but for now it's around about 500 nanometers. See, there's plenty of estimates to know. Speed of sound, estimates 340. Speed of instrumented waves, 3 times 10 to the 8. Density of water, 1,000. Density of air, probably say 1 would be acceptable for density of air. 3 is probably a bit too precise. Young's modulus, something times 10 to the 11 pascals. And atmospheric pressure, about 10 to the 5 pascals. Now what we're looking at here is convention of labeling stuff for axes and table columns. This is very important in your practical exams and so on. It's also important in your exams, normal exams. So this is a table, and what we've done is we've labelled the velocity by then dividing out the units. Okay, so what we're saying here is because we've got a velocity with a certain unit, which is ms to the -1, and we've divided it by its unit, we can then say that the rest of the table can be unitless. So same thing here, we've got time measured in seconds divided by seconds, means that this table can be unitless. Now something that's very important here is as you go down columns, you must always go to the same decimal place. Okay, it's all very important. What we have over here is the labeling for a graph, and it's a similar thing. We've got s squared divided by s squared, and that actually means that all the numbers down this column don't have to have a unit. You'll notice here that we haven't started from 0. You can start from any number you like in graphing and physics. even on the y-axis. Don't even have to do compressed axes. In fact, we prefer you not to do compressed axes. You notice we have a big triangle to find the gradient. That's also something you should do.
Da, 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 da.